The next property is a self-similarity property. Let me give the definition of self-similarity. Then we conclude linear process is a 1/2 self-similar. What is the definition of self-similar? A stochastic process is said to be H self-similar for some H greater than 0 if each finite dimensional random vector satisfying the condition for every t greater than 0, any choice of ti's for I is equal to 1 to n, the joint distribution for n dimension random variable at the time points t1, t2, tn multiplied by t times h for every t, and h is the h self-similar for some h greater than 0. If that distribution is same as x of the time point is multiplied by t without h in the whole right hand side. So if the joint distribution t times h1 for the random variable x, t times t2 for the second random variable, and so on, if this joint distribution is same as the joint distribution of this form, then we say it is a h self-similar for some h for every t greater than 0. One can verify the linear process is the 0.5 self-similar. Here I have not given the proof, but you can multiply for some t for h is 0.5, you can conclude the linear process is the 0.5 self-similar. The next property, that is very important one, that is Markov property. You know the definition of Markov property. So this is the definition of a Markov property. If any stochastic process satisfies the Markov property for arbitrary time point t0 to tn, which is less than t, if this condition is satisfied, then the stochastic process will be a Markov process. So here from the definition one can conclude w of t plus s minus w of s is independent of past, or alternatively, if you know ws equal to x naught, then no further knowledge of the value w of tau, where tau is less than s, has any effect on the knowledge of a probability law governing w t plus s minus ws. The whole time scale, the w of t plus s minus ws, which is independent of the whole past history, and if you know the information at the s, depends only at the time point s, not the whole past history. From the definition you can make out, because the definition says the increments are independent. Therefore, the w of t plus s minus ws is independent of the whole past information from 0 to s. That's what it says. Therefore, given wt, the future w of t plus h for any h greater than 0 only depends on the future increment w of t plus h minus wt, and this future is independent of past. Hence, this Markov property is satisfied. Since Markov property is satisfied for arbitrary time points t0 to tn, therefore this stochastic process is called a Markov process. So hence the Brownian motion is a Markov process. The next one is a Gaussian process. First let me define what is Gaussian process, then I am going to relate the Gaussian process with the Brownian motion. A stochastic process is called a Gaussian process if the distribution of each finite dimensional random vector is a multivariate Gaussian distributed. That means if you have a stochastic process and if you take any finite dimensional random vector from that stochastic process, if that finite dimensional random vector is a multivariate Gaussian distributed random vector, then the underlying stochastic process is a Gaussian process. Since for each finite dimensional random vector is a multivariate, you can write down the joint probability density function of n-dimensional random vector of Gaussian process. That is nothing but this is a joint probability density function, that is 1 divided by 2 power pi power n by 2. You find out the determinant of the matrix, and after that you find out the square root, then exponential of this one, where mu can be written as the vector and elements are nothing but the expectations. And this notation sum is the covariance matrix. Covariance between any two random variables x of ti's with x of tj's, where each one is running from 1 to n. Therefore, it is the square matrix. And the elements are nothing but the covariance between any two random variables. And all the diagonals will be the variance of x of ti's, where I is running from 1 to n. And it will be a symmetric matrix because covariance of x of ti comma x of tj is same as covariance of x of tj comma x of ti. Therefore, this matrix is a symmetric matrix and the diagonal elements are variance of x of ti's. So, one can find out the covariance of any two random variable using this formula. Since the WT is a Markov process as well as Gaussian process, you can write down the conditional CDF. The conditional CDF is same as the difference divided is less than or equal to x minus xn, but since this is normally distributed, WT minus W of xn is a normally distributed, therefore this is nothing but minus infinity to x minus xn, and this is a probability density function of a normally distributed random variable with mean 0 and the variance t minus t. Whenever we discuss the Brownian motion, we are discussing a standard Brownian motion with the Wt is equal to W0 is equal to 0 and mu is equal to 0 and sigma square is 1. Now we can discuss the Kolmogorov equation for the Brownian motion. We know that the Brownian motion is the Markov process with the continuous time and the continuous state space. We can write down what is the transition probability density. So the transition probability density P will be probability that Wt lies between x to x plus delta x Tx, given that W is equal to x naught. We make the following assumptions. For any delta greater than 0, the probability of absolute Wt minus Ws, which is greater than delta, given that W is equal to x, that is the order of t minus s. In other words, the small changes occurs during small intervals of time. That is the meaning of the above equation. Now we can find out the conditional expectation of Wt plus delta t minus Wt given Wt is equal to x divided by delta t as limit delta t tends to 0. That is nothing but you can note down as the denoted as the a of t comma x. This will be a function of t comma x, that is denoted as the a of t comma x. Similarly, you can make out the conditional expectation of the whole square given that Wt is equal to x, that you can denote it as the b of t comma x. In other words, the limit of infinitesimal mean of variance of the increment Wt exists and is equal to b of t comma x, which is known as the diffusion coefficient. So, a Markov process Wt satisfying the above conditions is known as a diffusion process, and the partial differential equation satisfied by its transition probability density function is known as a diffusion equation. The partial differential equation satisfied by its transition probability density function is known as a diffusion equation. So, this is the diffusion equation. This is a PDE for the transition probability density function P, and where A and B are earlier defined. And this equation is also known as a forward Kolmogorov equation and also known as a Fokker-Planck equation. And this equation is possible because of the Wt is a Markov process. Therefore, and also it is a Gaussian process. Therefore, we land up the transition probability density function P and satisfying the PDE, and this PDE is called the Fokker-Planck equation. If you solve the PDE, which is given here, for the standard Brownian motion, or the standard means W0 is equal to 0, mu is equal to 0, and sigma square is 1 in the definition of a Brownian motion. Then you will get the transition probability density function P is 1 divided by square root of 2 times pi t exponential of minus x square by 2 times t. And this is the probability density function of a standard normal distributed random variable with the mean 0 and the variance t. And the corresponding diffusion equation is dou p by dou t is equal to 1 by 2 dou square p by dou x square. Now we are going to discuss the joint distribution of a linear process. The way we discuss the Gaussian process, because in the Gaussian process, every finite dimensional random vector is a multivariate normally distributed random variable. Therefore, you can find out the joint distribution of W of T1 with W of T2. We know that W of T1 and W of T2 minus W of T1 are independent. Here we made T1 is less than T2. And also we know that W of T1 is normally distributed with the mean 0 variance T1. And this difference is also normally distributed with the mean 0 and the variance T2 minus T1, and both are independent. So our interest is to find out the joint distribution of W of T1 with W of T2. But for that, first we find out the joint distribution of W of T1 with W of T2 minus W of T1. Then use the function of random variables rule. Then you can find out the joint distribution of these two. So so that is the way. Here I have not given the derivation. So finally you will get the joint distribution of joint probability density function of W of T1 with W of T2 is in this form, where the probability density function is going to be the normally distributed random variable. Hence the joint distribution will be 1 divided by 2 pi times square root of T1 times T2 minus T1 exponential of this expression. Note that W of T1 and W of T2 are not independent, whereas W of T1 with W of T2 minus W of T1 are independent random variables. So using that we are finding the joint distribution of W of T1 with the W of T2. Once you know the joint distribution for any two random variables, the same way you can find out the joint distribution of any n random variables in the linear process also in the same way. I have not given the derivation here, and we can find out the joint distribution, joint probability density function of n random variables also. And we need a covariance matrix and expectation vector. So the expectation vector, that is mean, therefore all the means are 0, whereas the covariance, already we got the covariance of any two random variables of W of T1 with the W of Ti's with the W of Tj's. It will be a symmetric matrix and the diagonals are nothing but the variance of W. We can go for the multidimensional Brownian motion. We can have a W1 is a Brownian motion, W2 is another Brownian motion. So you can collect it as a, make it as another Wt, and each W is a one-dimensional Brownian motion. And you can go for the stochastic process are independent, therefore you will have a n-dimensional Brownian motion also. Here is the reference. So in this lecture we have discussed the definition of Brownian motion, and also we discussed the derivation of Brownian motion, and we have discussed important properties of Brownian motion, starting from stationary increment, increments are independent, Markov property, Martingale property, and also finally we discussed the multidimensional Brownian motion.